Hi, this video is about differentiating a function from the definition of the derivative. We have a question here. Find the derivatives of the following functions using the definition. And we're given three functions. Well, the definition of the derivative is here. The derivative of a function f at a point x is the limit as h approaches 0 of f of x plus h minus f of x all over h, if this limit exists. If the limit doesn't exist, we say that f is not differentiable at the point x. So to differentiate using the definition just means to evaluate this limit. So looking at part A, we have f1 of x equals 2x cubed. So its derivative is f1 dashed of x, which equals the limit as h approaches 0 of f1 of x plus h minus f1 of x all over h. And that's just copying from the definition. That equals the limit as h approaches 0, and we substitute in our values for this function. We get 2 times x plus h cubed minus 2x cubed all over h. Next we expand this term and we get the limit as h approaches 0 of 2 times x cubed plus 3x squared h plus 3xh squared plus h cubed minus 2x cubed all over h. Okay, we have 2x cubed minus 2x cubed, that's 0, and all the other terms have a factor of h, which we can cancel with the h in the denominator. So we get the limit as h approaches 0 of 2 times 3x squared, that's 6x squared, plus 2 times 3xh, that's 6xh, plus 2h squared, that's 2h squared. Okay, we can easily evaluate this limit now. The middle term goes to 0, so does the last term. So we just have 6x squared. And we can check this by going back to the function and differentiating the function directly. We can see that 6x squared is the correct derivative. And that's always a good idea when differentiating using the definition, to check your answer by going back and differentiating the function in the normal way. Well, f1 is a polynomial function, and for any other polynomial function this method of differentiating works just as well, and it usually doesn't present too many difficulties. So let's look at part B now. We have f2 of x equals the square root of x plus 1. So its derivative, f2 dashed of x, equals the limit as h approaches 0 of f2 of x plus h minus f2 of x all over h. We substitute in our values for this function. We get the limit as h approaches 0 of the square root of x plus h plus 1 minus square root of x plus 1 all over h. Well, this numerator is not so easy to simplify as it was in part A because of these square root signs. So we need to get rid of the square root signs, and we can do that by multiplying by this fraction, square root of x plus h plus 1 plus square root of x plus 1 all over the same expression, square root of x plus h plus 1 plus square root of x plus 1. So in effect we're only multiplying by 1 here. Now you might recognize this product of numerators here by the formula for real numbers a and b, a minus b times a plus b equals a squared minus b squared. So if we go ahead and do this multiplication, we get the limit as h approaches 0 of x plus h plus 1 minus x plus 1 all over h times square root of x plus h plus 1 plus square root of x plus 1. Now we can simplify the numerator. We get the limit as h approaches 0. We have x plus 1 minus x plus 1, which is 0, and we have h, which we can cancel with the h in the denominator. So we have 1 over square root of x plus h plus 1 plus square root of x plus 1. And we can evaluate this limit now. This first term, the h goes to 0, so we have square root of x plus 1 plus another square root of x plus 1. That's 2 of them. So we have 1 over 2 times the square root of x plus 1. And again, we can check this answer by going back to F2 and differentiating directly. Well, this method we've used here can be used for other functions involving square roots, such as f of x equals 1 over the square root of x plus 1, or just 1 over the square root of x. Okay, we'll look at part C now. We have f3 of x equals x to the 1/3. So its derivative, f3 dashed of x equals the limit as h approaches 0 of f3 of x plus h minus f3 of x all over h. We substitute in our values for the function. We get the limit as h approaches 0 of x plus h to the 1/3 minus x to the 1/3 all over h. Now again, we have a numerator that's not easy to simplify, so we might think about using the same formula as we did here, which would give us x plus h to the 1/3 plus x to the 1/3. But if we multiply this term by this term, we only get x plus h to the 2/3, which is not very good, so we might need to backtrack here, and we'll try an exponent of 2/3. So if we multiply this term by this term, then we get x plus h, which is what we want. But it introduces a cross term of x to the 1/3 times x plus h to the 2/3. And we need to cancel that with a term here, which we multiply with this. So it needs to be x plus h to the 1/3 times x to the 1/3. Now this introduces a further cross term when multiplied by this. So we need another term to cancel that, and it needs to be x to the 2/3. And then finally we get the term of x to the 1/3 times x to the 2/3, which is x, which is a good result. We put that all over the same expression to make sure that we're multiplying only by 1. Now we perform the multiplication here. We get the limit as h approaches 0 of x plus h minus x all over h times x plus h to the 2/3 plus x plus h to the 1/3 times x to the 1/3 plus x to the 2/3. And we simplify the numerator here. The x's cancel, leaving an h, which we cancel with the h in the denominator. So we get the limit as h approaches 0 of 1 over x plus h to the 2/3 plus x plus h to the 1/3 times x to the 1/3 plus x to the 2/3. Okay, we can evaluate this limit now. This term goes to x to the 2/3, so does this middle term, and so does the last term, so there's 3 of them. So we have 1 over 3 times x to the 2/3. And again, we can verify this answer by going back to F3 and differentiating it directly. Okay, well, there's some of the techniques you can use to differentiate various functions of x. If you have any questions or comments, please leave a comment below, and thanks for watching.